that several company stock, apparently the whole industry stock, went down 60%. And then I'm starting to learn about this, and my first reaction was, I didn't know they were public. How could a quantum computer company be public? And anyhow, I discovered they were public companies. I'm very happy for them. And yes, I'm very happy for them. So I said, listen, the world's got this wrong. Let's invite all of those companies and more, the quantum computing industry, and to the extent that they don't bring cabbages and apples and stuff that they can throw at me, to the extent that this would be an extraordinary moment, that we can learn about the state of the art of quantum computing. There are so many different approaches: trapped ion, neutral atoms, superconducting qubits, topological qubits. You have quantum annealing, photonics. I mean, there's so many different ways of addressing this that I thought, wouldn't it be amazing if the CEOs, the technology leaders, the companies that are leading this pioneering technology were coming together for the very first time to talk about it, and of course, in the process, they could explain why I was wrong. This is going to be the first event in history where a company CEO invites all of the guests to explain why he was wrong.
So he just said he was wrong?
But I don't know.
Closer. Oh, maybe he's not.
So that's what makes this movie so great. That's what makes this event so great. Anyhow, we don't make quantum computers. Nvidia doesn't make quantum computers. But we dedicate ourselves to creating accelerated computing stacks to enable quantum computers. We do the same with self-driving cars. As you know, Nvidia is probably more integrated into the world of automobiles and autonomous vehicles, and we work with just about everybody in some way to advance autonomous vehicles, and yet we don't build cars. Nvidia has a broad range of technologies and product offerings and libraries and computers. We call it the 3-computer solution to help advance robotics in all forms. Facility robotics, factories that are going to be robotics to build, orchestrate robots that are going to build products that are robotic. Incredibly complicated set of computing and libraries and algorithms and models, and we approach it in a way as if we are deeply integrated into the ecosystem and in industry, and we care deeply about them, and yet we don't build robots. We don't build quantum computers, but we are deeply integrated into the quantum computing industry, and we create libraries. CUDA-Q is a programming model for hybrid classical accelerated quantum. We have cuQuantum libraries that help you simulate quantum circuits, and DGX Quantum to do error correction of quantum computers. We partner with them, we support them, we help them in any possible way, and but try not to say anything that trips them up every now and then. And so, anyways, we care deeply about this ecosystem, and I'm really happy to bring our partners, many of our friends. There are many that are not here, and the reason for that is because we had to do this in 3 panels. There were so many people. The quantum computing industry, as you know, a new computing platform is not easy to create, and we didn't create CUDA computing ourselves. We created the architecture, of course, we created the computers, we dedicated ourselves to a very long roadmap of compatibility and dedication to helping developers and creating libraries and tools and evangelizing and so on and so forth. But in the final analysis, the CUDA accelerated computing ecosystem was built by all of us. That's what GTC is about. In a lot of ways, this is just the beginning of the quantum computing ecosystem. And it's really terrific to be able to celebrate it with all of our friends and partners. And so I'm going to invite many of them on stage. I just want to let you know that there were many that we couldn't, and I want to thank all of you for your partnership and your friendship. And and we'll try to invite you next time. But before I do that, we're making an announcement. I'm making an announcement today that Nvidia is starting. Now, I'm saying this as if this announcement is coming as a result of. I just want to let you know that we were going to make this announcement before this. Okay, so you don't make it. The cause and effect, physics matter here. Okay, the cause and effect is, in this case, is completely unrelated. We're announcing that Nvidia we're going to open a quantum research lab in Boston. It's going to have a, yep. It will likely be the most advanced accelerated computing, hybrid quantum computing research lab in the world. And it's going to be located in Boston so that we could partner with Harvard and MIT. And some of our partners are going to be in there initially, but many others will be working in this quantum research lab in the long term. Quantinuum, Quantum Machines, and QA are going to be the inaugural partners with us to build this quantum research lab. And so I'm very happy about that. And we're going to get that going as soon as possible. And so now what I'm going to do is I'm going to introduce some of my CEO colleagues, and please join me to welcome them. Alan Baratz, D-Wave. Alan. Peter Chapman, IonQ. Peter, thank you. Let's see. I think the next one is Loic. Henriette, I think, right? Isn't it Loic? Okay. Welcome. And Rajiv Hazra, Quantinuum. Rajiv. And Subodh. Subodh, come on stage. We're Getty.
Getty CEO.
Nice to see you. So I guess the first thing is sorry about that. That was funny. That was, for everybody. We do? Hang on a second. Come on, Mikhail. Goodness gracious. I left Cuera behind. Sorry about that. So it reminds me of a joke. It reminds me of a short story. This is nothing like you. So anyways, I was left behind. This was in 1995, and we had just started Nvidia, the 3D graphics ecosystem, whole bunch of 3D graphics companies. It was like a new 3D graphics company per week, and we were the first one to start. But after a couple of years, there were like 50, 60 competitors. And we created an architecture which we chose a technology which was exactly wrong, okay? And so even though we were the first company to start, because our technology was exactly wrong, we were about to go out of business. And this financial analyst, industry analyst that follows the industry, he kept a list of all the companies that were building 3D graphics. And so anyways, and it was being published every single week, and then one week it came out and we were left off that list. And so I was left behind, and I said, why'd you leave us off the list? He said, well, I thought you guys went out of business. But you guys are doing great, sorry about that.
Great story, great story.
All right. So listen. Each one of you some of you have chosen different approaches. I mean, there are quite a few different approaches to quantum computing, and maybe what we could do is we start by having each one of you, and just remember there are a whole bunch of us. So each one of you take a moment and talk about your approach and why you did it. And Mikhail, since I almost left you behind, why don't you start?
Thank you. So first off, thank you for hosting us. It's amazing to be here.
Thank you.
Also thank you for your contribution to this emerging quantum ecosystem. So we are building quantum computers literally from single atoms. And we assemble them and control them using arrays of laser beams, using basically techniques like holography techniques similar to those used to project, for example, to beam the computer kind of images to the big screens. And the key advantages is that the atoms are basically God-given qubits. They're all identical. They're extremely well isolated. We can preserve quantum states for a very long time. But also, we can use light, we can use lasers to control these atoms, basically position them at will and move them around, including both during the computation process itself. And in particular, it allows us to build a processor where connectivity is basically a living organism. It evolves during computation itself, and this is very special. So this allows us to build systems now which have thousands of qubits. It allows us to deploy for the first time these techniques of error correction, which you mentioned, and execute algorithms with this so-called protected logical qubits.
Yeah, that's great.
And this is, it's a very special approach, and we're in a very special time using this approach.
Yeah. Thank you, Mikhail. Go ahead. Let's take turns. Go ahead.
So thank you for the opportunity. So at Rigetti Computing, we develop superconducting gate-based quantum computers. We are based in Berkeley here, and we also have a fab in Fremont. So why superconducting gate-based quantum computing? Gate-based because that's how we know how to do the broad world of computing. That's how classical computers run. Why superconducting? That's an area where, along with us, there are many other companies, including some big companies like IBM, Google, Amazon, as well as the government of China is investing heavily in superconducting gate-based computing. The reason we like superconducting is primarily because of its advantages in scalability and gate speeds. We are using fundamentally a silicon chip, so we know how to scale up because of the leverage of semiconductor industry and 5 decades of experience there. And because we are dealing with electrons, our gate speeds are in tens of nanoseconds, and that makes it very easily compatible with the CPU, GPU ecosystem, which is the way we think quantum computing is going to come along. So we feel very good about scalability and gate speed. The challenge and Achilles heel, if you will, of superconducting quantum computing has always been fidelity. We get noise because of this intrinsically engineered devices in the chips, just like CMOS technology. And historically, that was in the low 90s and mid 90s when the qubits entangle with each other. The 2-qubit gate fidelity is what we call it. What's been exciting is in the last few months, ourselves, along with some other companies in superconducting like IBM and Google, have made some very important strides. And now we are in the 99 to 99.5% 2-qubit gate fidelity, which is comparable with the best over here with pure atoms and other areas. So we maintain the advantages of scalability and gate speed, but now we feel very good about where we are with fidelity. So that makes it a lot more attractive. Within this space, Rigetti, we differentiate ourselves by an open modular approach. So we have designed our stack, so if we find a more creative solution out there, whether it's an error correction from a company like Riverlane or CUDA-Q from Nvidia, or quantum machines for control systems, we can easily integrate that into our stack, as opposed to some other companies like IBM or Google who have designed it in a mainframe approach. We believe an open modular approach is the right way to build an ecosystem while we are in R&D. So in the overall journey, our flagship system is an 84-qubit system with 70 nanosecond gate speed. It's available to anyone on AWS and Azure right now. We believe it's one of the best. But frankly, it's not good enough yet for any practical use, as we talked about earlier. And we think we are roughly—
Well, don't give up yet. Don't give up yet. Here, Rajiv, why don't you start?
Thanks, Jensen, for hosting us. Yeah. So at Quantinuum, we build quantum computers using the trapped ion modality, as it's called, and a particular architectural approach called QCCD, or quantum charge coupled device. The beauty of this approach is it produces the industry's highest fidelities, 999s and beyond.
And there are a lot of challenges in quantum computing, as you know. However, coherence time, scalability, fidelity, these are some of the most challenging properties. And as you're thinking about and listening to these different quantum computing approaches, just listen for those words. I think they're consistently being used anyhow, and it helps you understand the pros and cons or the challenges and the opportunities associated with each one of the technologies. Okay, go ahead, Rajiv.
So thank you for filling it in. Basically, we have the industry's highest fidelity. Our approach is to extend.
Just a friendly reminder for you guys. I think Jensen's saying it sounds like they're talking very, very advanced. And most people, investors, people watching, don't understand unless they use like a grade 4 reading level. And so when they're just talking really, really, really advanced, there's nothing that really triggers investor positive sentiment. They just hear a lot of complicated stuff. So that's why maybe the market's not responding well right now to this event so far, because there hasn't been any clear narrative around quantum. They're just talking about the problems they're dealing with and super high level detailed narrative. So that's probably why it's not doing well. So let's jump back in.
Else is out in the industry today. That is a beautiful compliment.
Well, welcome to GTC. We have a lot of hairy problems here. All right, so thank you, Rajiv. Yeah, Lloyd, go ahead.
Yeah, thanks a lot for hosting us. At Pascal, we build quantum processors that leverage the neutral atom technology. So quite close to what Michel Lukin and Quera is doing. This technology has several key advantages, like scalability. We can trap and control many of those qubits right now, thousands of them. And also, it's easy to control them with laser light. And it's a relatively recent technology compared to trapped ions and superconducting qubits to develop quantum computers. Actually, it's more recent, but there is a lot of progress and a lot of momentum in terms of gate fidelities and scaling of this approach. At Pascal, what we are also committed to doing is working very strongly on engineering of those devices to turn them from lab experiments to real industrial products. I think we all agree here that usage and adoption is very key for the entire quantum community right now. And at Pascal, we really want to deliver on that promise. So over the past 18 months, we'll have delivered 4 machines worldwide, including one in France, and CEA, Gency, and another one in Germany, Jülich Supercomputing Center. So that's about it for Pascal. We work with neutral atoms and focusing very strongly on engineering.
That's terrific. Thank you. Go ahead, Peter. Please tell us about your company.
So I'm the chairman for IonQ. We're a trapped ion company like Continuum. Trapped ions actually were used back in 1995 when they were looking at atomic clocks. Atomic clocks and our technology have a huge overlap. And back in 1995, a team at NIST and one of the co-founders of IonQ did the first ever quantum logic gates. And all of this craziness that you see coming all started in 1995 from that experiment. So we're now 30 years into this investment in trapped ions. So very similar to other modalities, we use individual atoms and we use lasers to do computation. We're down at 0.02 nanometers. So when you look at the silicon industry, they're way, way up there compared to where we play. We play with individual atoms. So these, the advantages to our technology is one is you can have a room temperature quantum computer. So it can fit in a rack, and to be honest, it looks kind of boring compared to what you probably imagine, because it'll be rack-based room temperature. The other advantage, because we use optics and lasers, is that you can network them together to do distributed quantum computing to get to larger numbers of qubits. And you can reuse the existing infrastructure of the internet using fiber optics. And then as has been mentioned, trapped ions have the best average 2-qubit gate fidelities. And so in that sense, they lead in, and that's a fairly large advantage because it means that the amount of error correction that you need to do will be less than maybe some other modalities. But each one of, and I just say since 1995, it's amazing how many different modalities have showed up, free qubits, and the amount of progress that's been made. So it's really quite exciting from that point of view. And it's great to see the leading companies on stage here today with us. So.
Yeah, thank you, Peter. Alan, go ahead.
Thanks, Jensen. So we are a superconducting company, similar to Rigetti. We believe that superconducting provides the best balance between qubit fidelity, or the quality of the qubits, and gate speeds, time to compute. But we're actually quite unique from everybody else on this panel and pretty much everybody else in the industry because we use annealing technology as opposed to gate model technology. Without going into the details, annealing is a much easier technology to work with. It's easier to scale. It's much less sensitive to noise and errors. And probably the best proof point for that was in a paper that we published in Science last week, where we performed a useful computation, properties of magnetic materials, that would take nearly 1 million years to compute classically. And then this week, we actually put a paper on the archive where we showed how to use that computation to create quantum proof of work in a blockchain. So the idea would be that you would use the quantum computer to create the hashing function, and you would use the quantum computer to validate the hashing function. And we now have this running on 4 of our quantum computers as the first distributed quantum application, where, in fact, we're generating hashes, we're validating hashes, and we think this could be a very interesting, much lower energy consumption approach to blockchain.
Mm-hmm. You know, every time that somebody in the quantum computing industry achieves a milestone, it stirs up a fair amount of controversy among the others. Did you stir up any controversy in your achievement? Because at the moment, I think the achievement to controversy ratio is literally 1 to 1.
So the answer to the question is that I've received a lot of positive feedback from my colleagues in the industry.
It was exactly like me when I did.
That having been said, and only since you asked, and I don't like to name names, but I will, there was a paper that came out of some researchers at the Flatiron Institute in New York. This is a really solid research team. And what they were able to do was advance the state of the art on a classical computation in tensor networks. And what they've been able to do is to show that for the smallest instances that we computed, which we also computed classically on GPU clusters, they could do it a little bit faster. Now, they made some claims about how that undermines the results, but not at all. I mean, we computed multiple lattices, multiple size lattices, multiple evolution timeframes, multiple properties on the lattice, and so this is a very strong result. It's actually been in the public domain for over a year now.
Mm-hmm. Yeah, that's terrific. So I guess the question that stirred up a fair amount of excitement is really about what is the definition of usefulness of quantum computing, and when do we expect that? Before we answer to when do we expect that, maybe we'll build up to it. What are some of the early applications you think, and we'll start back in Mikhail again, what are some of the early applications you think that'd be worthy of the endeavor of a quantum computer, number one, and number two, how do you define usefulness?
So maybe I will start kind of at a high level. So quantum computer is really a fundamentally new scientific and engineering tool. And if you look at the history of science and technology, whenever you come up with a new tool, the first thing that you use it is to really kind of advance the science and actually make scientific discoveries. And in fact, quantum computers literally allows us to go into corners of universe where we have never been. And if you go to these corners responsibly, you always find something interesting. So, and what kind of I mean by that is that I believe there is a huge potential to use the machines which are either existing already now or kind of which are being developed in the near term to really kind of advance this kind of scientific frontier and actually make new discoveries. There has been already discoveries made using quantum computers, but to be maximally honest, there were very few. And the way how many of us kind of are thinking about is that now we are in the era of this kind of quantum discovery where we can use these machines to actually really, mostly kind of exploring physics of complex systems, maybe of, related to things like also chemistry, material science, and the field is now really ripe for using these machines to kind of really to really push into this kind of science directions and really start making discoveries. Often they are things which maybe are not.
Here's a problem that I see here. I got to cut this off. I'm going to keep the video going, so it's fine. But when you look at this narrative, it's really hard to understand the CEOs when they talk so technically that it's hard to hear how they're like really like they need to talk like grade 4 or something, because I don't understand always when they go so technical. And maybe I'm dumb, but like as an investor watching that, I feel like that's really important.
And then so that's a trapped ion perspective. What about a superconducting perspective?
It's a neutral atom perspective.
Neutral atom.
It's a small differentiation.
Sorry. Yeah, sorry.
So following on what you were saying, I mean, I agreed with every area that the fundamental premise that scientific discovery is going to be taken to a new frontier. But we're seeing applications today. As I said, we kind of focus on what is the big problem for a customer or a partner we want to solve. We are seeing applications in the area of chemistry on, how do you get to new refrigerants, right, that have certain sustainable properties. How do you generate hydrogen from water more efficiently without needing platinum as a catalyst for the reaction? In biology, we are looking at how peptides bind, right? So these are very specific instances, and doing that gives us a good way to understand two things. What algorithms do you need to attack it with? And then what capability you need in the machines at a certain point in time. And you asked the question of what is the performance standard? Like, I come from a classical background. You had performance per watt, then you had performance per watt per dollar. We're getting to a point where if you look at it through the lens of big problems you want to fundamentally solve with the figure of merit of either solving it more accurately or solving it more accurately and with less energy and cost, then we are getting to the point of what is your scale of computation. That's usually qubits, number of qubits, but also what fidelities and error rates you can sustain to make those qubits useful, right? I'm not saying there's a perfect ratio of those things, but they're generally leading us to say how useful is your powerful quantum computer. And that can only be done through the lens of looking at big problems and saying, how do you solve them? With the help of a quantum computer, not necessarily replacing a classical computer with a quantum computer.
Yeah, Rajiv, one of the areas that I do wonder is whether quantum computing is just simply poorly positioned. And let me take a swing at it. There are so many things in industry which is built on fundamental sciences, and quantum computers, in its broadest sense, can be the ultimate instrument for understanding the basic sciences that affects that industry. However, because it was described as a quantum computer instead of a quantum instrument, people have a notion about what a computer is. It should be able to run Excel super fast, and you know that every respectable computer should be able to run Crisis, the game. And so there's a common sense about what a computer is, and it's attached to memory, it's attached to network, it's got storage, it should be able to read and write, and there's a programming model associated with the computer that I wonder if it's just the wrong wrong mental model. And as a scientific instrument, it's extraordinary, Mikhail, as you say, and that the opportunity to understand science deeper along the way is extraordinary. But to position it as a computer per se, and to hold it to the standards of a computer per se, that we all understand, what is. I wonder if that could be a reframing and allows this entire industry to be much further along, frankly, in that reframing as a scientific instrument for very important industries. And go ahead.
Yeah, I totally agree with what you said. In some sense, the word quantum computer is misleading because people expect that you can replace a computer, a classical computer, with a quantum one. It's not like that. It's more like very complementary. We like to call our machines like quantum processors, like very specialized machines that you can use in a complex workflow alongside CPUs and GPUs, but really for specialized tasks. And I think everyone agrees on that particular way of using quantum computers, quantum processors. It would be easier to work alongside classical and not working towards replacing all the compute capacities that are in place right now.
So I'm actually struggling with the concept. I don't know how to think of a quantum computer as an instrument when it's being used for materials discovery, when it's being used for blockchain, when it's being used NTT Docomo to improve cell tower resource utilization. I mean, it's true that there are many applications I would never try to run on a quantum computer. But for applications that require extensive processing power, these machines are very powerful, and I think go well beyond just instrumentation or measurement. Sorry.
I'll jump in.
It's okay. Yeah.
I'll jump in on that.
I was actually just trying to help.
We saw your help.
Let me tell you the mistake. This whole session is going to be like a therapy session for me. So a long time ago, somebody asked me, so what's accelerated computing good for? And I said a long time ago, because I was wrong, that this is going to replace computers. This is going to be the way computing is done, and everything's going to be better. And it turned out I was number one wrong and unnecessarily wrong. It's better to be narrowly focused on something and be extraordinarily good at it. But the moment you cross that line and start talking about the traveling salesperson problem, then it became unnecessary. Because that problem is obviously being solved as we know it today. And Uber cars taxis are showing up. Maybe they're three seconds late or 30 seconds late or whatever it is, but they show up. And I do think that I wonder if we hold ourselves to a bar to solve a problem that's unnecessary for quantum computers to solve, quite frankly, to change the world. And it takes focus away from something that you uniquely do, and quite frankly, sooner than later. Anyways, that was just my swing at it. Go ahead, Peter.
Well, here at the show, we actually have several applications which are showing quantum as now. One of them is with ANSYS, and you might know one of their products, which is LS-DYNA, and runs obviously with GPUs today. We announced that we've integrated our quantum computers with LS-DYNA and a 12% increase in performance in modeling a blood pump. And so this is the first time actually quantum with production software. We also announced with Nvidia, AWS, and AstraZeneca a 20x improvement in a chemistry application. What's amazing about it is that we did that on 36 qubits, our existing system today. By the end of the year, we will have 64 qubits. Every time you add a qubit, you double the computational power. So that's 2 to the 28 increase in a single generation of chip, which is roughly 260 million times more powerful. So by the end of the year, one would expect for things like LS-DYNA and for chemistry applications to suddenly have huge performance increases. And so we're working right now on these applications, which, to be honest, probably all of you use, to now be able to have significant impact using a quantum computer. I do think that your statement about 10 years is, we think of ourselves as like 10 years, where you were 10 years ago. We hope that obviously 10 years from now, we'll be up there with Nvidia as well in a rarefied club. So, but it does take a long time to go from, you know, it's kind of a startup to where you are today. And it's completely fine to sit down and say for the computer industry, for the quantum industry, it's going to be another 10 to 15 years to get to where Nvidia and all the other giants are. It's just not going to start then. It's going to start, it's starting today.
You're going to be much, much larger than Nvidia. There's no, we're going to be a relic of the past. All right, so if it seems like one of the things that's really interesting is that there are so many different approaches to quantum computing, and it is so diverse in its approaches. Why is it that this industry doesn't quickly discover a more promising approach as you see each other's work, and naturally, you know, through evolution, people select the best approach, and then everybody started to advance the whole industry in a unified way much more quickly. You know, as I observe this industry, it's surprisingly diverse, and there's thousands of flowers blooming. You know, when does it become a garden?
I'll just say actually, if you look across us today, there's a number of people you heard are using individual atoms, lasers, and all the rest. And so we actually have more commonality than most people expect often. And so I would think that, I would hope that in the future that there is more sharing and maybe even the ability to work together, because the promise of quantum computing and what it can do for mankind is so significant. It's actually larger than any one of the companies that are here sitting on stage today. And so, you know, I think that mankind has a whole range of significant problems to be worked out, and we need quantum computing to be able to solve it. So we're still obviously new ways to be able to build qubits are being found every day, but I think that over the next couple of years, we will start to coalesce to probably 2, maybe 3 different approaches. And some of us will probably come together because we do share basically the underlying technology, and so it makes sense.
In many of the problems that you've described, the precise answer is not exactly known because, as you know, fluids are quite chaotic and hard to know exactly what the right answer is. And in those kind of examples, using AI for emulation can give you, you know, tens of thousands of X speed up, orders of magnitude speed up from where we are today with principal solvers. How do you guys think through that? What is the point of solving that problem when classical still has orders of magnitude of progress in the next couple of years ahead of it?
Well, there's orders of magnitude of progress, but at the same time, there are problems that are just, you know, impossible to solve classically today. You know, there are problems in the area of drug discovery, there are problems in the area of global weather modeling, but even just the application that I shared, which is the basis of our paper a week ago, which is computing properties of materials. You know, we use Frontier, which is basically one of your systems, massively parallel supercomputer at Oak Ridge National Lab, and would take millions of years to perform the computation. So the point is, there are still hard computational problems that are out of the reach of classical. And AI isn't going to address those problems either. They're just out of the reach of classical.
Right, exactly. Go ahead, Rajiv.
So I'd like to make, go ahead.
Sorry.
Go ahead.
Actually, it's interesting that it took us 30 minutes to get to AI, but from our point of view, where we see it quite interestingly is, and it's an extension to your question on whether we should call it a computer or not, is these quantum devices or tools or instruments, as you call them, are expanding the ability for us to access data to train these AI engines that previously was not possible. So if you're going to solve a chemistry problem, today, humankind's max ability is defined by things like density function theory or other approximations to the quantum space, the world of that information that we haven't had. That's like, to me, trying to train autonomous vehicles by giving them city grids of 500 feet squared and not having the detail of lanes or other things. So what we see is this concept of, computer brings in, I have a computer A versus a computer B. So A must run the thing faster than B for it to be better, at least technically, till you tell them what the price of the A is. We don't see it that way. We see it as what can A and B do. If A is established, classical, well-honed frontier models, how are we training those models? And are we enabling those models with the data so it can now continue to be agentic and continue to reason and continue to do things that otherwise we'd be pulled in back to do, right? And we call that Gen, not AI, Gen Q AI. And that's kind of breaks the paradigm of a computer competing with another computer. It's two computers now working together, two completely different ways, but they are input-output for each other. The output of the quantum computer is the input into these LLMs and the training methodologies, so you can have LLMs that actually understand things like ground state energy and ground state configurations of molecules, so you can then use them to start doing perturbation theory on, well, is this molecule going to last inside my body and deliver the drug at the right kinetic, paradigm or not? So that is how we see quantum as an addition of a tool or an instrument into what is already a developing and rapidly maturing and improving compute paradigm.
And in the few minutes we have here, what are the things that we could do in the world of accelerated classical to be helpful to all of you, so that we could advance your work much more rapidly?
So maybe I will start.
Can we? How about we start with in the middle?
Yeah. Okay.
Come on, Mr. Frenchman, let's go.
Yeah, thank you. Yeah, I guess it's very important, as was said earlier, to couple as best as possible the various compute modalities like classical and quantum. For the moment, it's not really a matter of bandwidth or really being able to collocate to be able to do things fast, because we're not there yet. It's not the pressing paradigm. At some point, it will be a problem, but not now. Now it's really about identifying the key problems, the key domains on which we can collaborate and leverage the best of both worlds. Mm-hmm. And I fully agree with what you said about actually using a quantum computer, a quantum processor, to process and to create data on a problem which is in itself quantum, that classical struggles with naturally. And then use that advantage, natural advantage, in a workflow that is larger with the CPUs and GPUs, and couple that quite well at the software level.
Mm-hmm. Mm-hmm.
I was just going to say, we use your GPUs to design our chips, to often do co-simulation to make sure that the quantum computers are working. It's when we look to the future for quantum computing, it's going to be a set of classical systems sitting right next to a quantum computer. And the two of them are going back and forth. Mm-hmm. And so it isn't something where one is replacing the other. They're working together. And then if you look at the same things that are doing today, we're applying machine learning to be able to figure out how to build optimization, not only for the quantum computers itself and how they run. So it is already a synergistic relationship between classical computing and the strange thing is our quantum computers are almost entirely classical, right? The only quantum part happens to be a little chip and a couple of atoms at the center. The rest of it is entirely classical. So it isn't going to replace. I wouldn't short any Nvidia stock at the end of this. So So I think you have a strong position going forward. But I would expect that in the future it will be a QPU, a GPU, and a CPU all working together to be able to solve it.
In fact, if I could just add a little something there, I think so first of all, you probably observe that Nvidia accelerated computing is the largest volume parallel computer the world's ever seen, and yet we don't call it a parallel computer. For that very reason. A long time ago, there was an industry called parallel computing, and it was opposed to sequential computing. And the mistake of that approach, the mistake of that positioning, is in fact, Amdahl's law doesn't work that way, and there's no reason to replace something that does an incredibly good job. You should add to it and ride the wave of the momentum that's been created for it. And so that's why we decided to call it an accelerated computing, but it's still a computer, and that really revolutionized how people thought about us and how we thought about ourselves and how we thought about our work, and I think the idea that this is a quantum computing industry or a quantum computer is less good than a quantum processor that's going to make every computer better, and so anyhow, go ahead, Rajiv. No, excuse me.
I was going to say that some of the paradigms have to change in the way we are thinking about quantum processing or quantum computing. Some people have observed that think of a human brain and how it works. And that's closer to a quantum computer than our conventional thinking of HPC and how HPC should be integrating with quantum computers. We are dealing with analog inputs. We are dealing with analog outputs. We are dealing with simultaneous multiple variables at the same time, exactly like the way human brain and our neurons work. So fundamentally, we may be limiting ourselves by thinking of quantum computing in the context of classical computing, and may have to start thinking broader and say, what are the kinds of things we could potentially envision when a quantum computer is brought in conjunction with HPC? And to your question, how can we accelerate quantum computing development with HPCs? At the same time, how can quantum computing help Gen AI get to AGI? Those are some of the trickier things that we could use quantum computer for.
Yeah. Well, this is going to be the beginning of a great conversation for the industry, and it's a great pleasure for me to host all of you. And this is just the first of many in our series, and I'm looking forward to. Mikhail wants to finish. You already.
Yes.
Yeah. Go ahead. Finish.
Yeah. So I think it's like these are all great examples, and I want to go back to kind of the point I made before. And so basically, quantum computer, in a sense of like computation, is not a hammer. It's like a scalpel. And it's a precision instrument. And what you basically want to do with that, and it's kind of our vision, if you really want to realize, large-scale useful applications, you have to think about this entire problem as a kind of co-design, where if you have a problem you want to solve, you want to basically solve as much as possible with the classical computers and identify hard quantum part, and then find an algorithm, find a good error correcting code, find the right compiler, find the right decoder, and it all has to be optimized with the specific architecture, quantum architecture in mind. And in all of this process, what you want to do, you want to basically outsource as much as possible, at least at this time, to a classical part. And this could be CPUs, GPUs, depending on what you want to do. And of course, at the end, you want to use an output of the quantum data, indeed, to train your models and improve them. That's how we see the real value of quantum computers emerging in the next couple of years.
That's surely one very productive use case. Yeah, thank you, guys. Okay, how about we just have to be very quick. We just have to be very quick. Next year, this time, what are we going to be talking about? And so let's just quickly go through. Go ahead, Alan. Next year, this time, what do you hope that we're talking about, so I remember it?
How quantum is helping you to do better model training and inference with lower power consumption.
Okay, go ahead, Peter.
All right, I guess I'm muted. Those comments from Jensen were a little bit fiery. What do you guys think? It seems like he was pointing towards firing some missiles over towards quantum computing, that it's still far away. I didn't really like the comments, but at the same time, it was a little bit of a troll. And then you see Alan's response. When Alan responded, you have this response related to, sorry, Jensen, that's where we're at, whether you like it or not. Kind of like, sorry. And Jensen, I don't know how he felt about it, but you can see there's some animosity between the quantum companies and Jensen while they're on stage. When it comes to quantum computing, which now maybe we refer to it as accelerated quantum, according to the definition of this conference, would indicate that we're looking at, you can see this overall uptrend on quantum. It's still up. 8% swing on Rigetti. QBTS was swinging about 14% today. We've seen these stocks swing 10, 20, or 30% in a day. So this isn't anything out of the ordinary. In fact, we could still see a bounce tomorrow if there's positive lights or coverage around this event. The other event that we have coming up here that we'll have to watch closely is this Qubits conference in Scottsdale, Arizona. If you guys are familiar, the Qubits conference essentially is in Scottsdale. It's from D-Wave, and they're going to be most likely having some events with Alan, the CEO, speaking a lot more there. If you guys want to stay up to date with the quantum accelerated market and the computing space, I would encourage you guys to subscribe. We just went to CES. We saw IONQ. We got to meet the executives from IBM and Microsoft, and we covered it in depth going there. We're also going to this Qubits conference later this month in Scottsdale, and we cover the quantum computing space, AI, and space tech stocks, as well as robotics. So if you guys want to stay up to date in that space, make sure to subscribe, like the video, and if you'd like to watch me trade live, we traded live this morning. We trade live every day, Monday through Friday in these markets. And if you want to watch me trade live, it's the second link below. Thank you guys so much for watching. Hit that like button if you enjoyed, and let's see if we can have some green days over the next few in the markets. I'll see you guys in the next video. Thanks so much for watching.